Yeah, it's 2:15. I guess we can start.
I'll start or wait for a minute more. I'll
Yeah,
start.
because we have 40, so I think yeah, we can start in a minute. Yeah.
Okay.
Saikia, I guess it's a 2:15, so you can start your lecture.
Okay, thank you. Thank you all. Okay, good afternoon to all of you. So we'll start by actually just showing you a couple of slides related to one of the questions which was asked yesterday, namely the ionization of the photons and the lines that you see or the line ratios that you determine, and that is related to the photons which are available. So I thought I would just show you pictures or two images of what the spectral energy distribution looks like. Okay, so in this figure, what you can see on the left is the spectral energy distribution. On the x-axis is the frequency, y-axis is actually nu f nu. Okay, not often only the flux is presented, but this is multiplied by nu, so you have energy over there. And what you see over here are the various components which contribute at different wavelengths largely. And even if you look at a starburst galaxy, which I'm running my cursor through, it doesn't really extend to the highest energies, as you can see largely, right? Whereas AGN, you can see these lines over here, which contributes from the accretion disk or the hot corona, or components of reflection, which Gulab talked to you about, that you have the energy distributions are quite different. And what you see also on the right-hand side, I've given the references below. In fact, the first reference has a video as well, a short video, which you can see, made by Hickox and Alexander, who wrote a review on this topic in annual reviews on the, and this figure actually shows you on the y-axis, the obscuration increases. Obscuration means basically absorption of the radiation, and hydrogen column density is what is given over here. So this is log of NH 10 to the power of 21, column density per centimeter squared, and this is 24. And on this side, the AGN dominance increases 0.3, and this is 3 over here. So you can also look at changes in spectral shape that one observes over here, depending on obscuration and the dominance of the active galactic nucleus. So what the kind of photons which we see in an AGN, as you can see, it extends to higher energies. And I thought I would just show you one more slide before continuing with today's presentation. And that is to look at just the spectral energy distributions from the ultraviolet to the infrared. Here actually wavelength is increasing this way. So frequency is increasing this way. And what you see over here are, this is a normal elliptical galaxy, normal disk galaxy. Don't worry about the lines over here too much. All I wanted to bring out is a kind of large infrared luminosities, which we talked about yesterday, and M82s over here, and the standard ultraluminous infrared galaxies over here, which is due to dust heated by the burst of star formation which has taken place, right? So this is just to add a little bit to what we discussed yesterday. So today what we will look at, before we get on to posing two questions, the two main questions that we'll pose today is that you have seen pictures of radio galaxies and quasars, and which are amongst the radio loud AGN, active galactic nuclei. So one question which we'll pose today is related to the jets. Joydeep has talked to you about launching of jets, and you have been introduced to AGN across different wavelengths, particularly X-rays by Gulab. But we will ask a very specific question about the jets being asymmetric or sometimes one-sided in a set of radio loud active galactic nuclei, while these jets, which are the signs of energy transport to the outer lobes, the jets are asymmetric while the outer lobes appear reasonably symmetric. We'll try to explore possible explanations for it. We'll try to see how that is sort of generally accepted now, and what are the evidences in favor of it. Then the second thing we will ask ourselves is that we talked about a diverse set of active galactic nuclei. And we'll ask ourselves whether this diversity is truly intrinsic, or do galaxies sometimes appear to be different because of the way they're inclined towards us, at what angle of lines of sight they're inclined towards us, and what are the manifestations of that? Is the true diversity a little less than what we observe when we look at the heavens? So these are the two questions we will try to answer. And before we do that, just a brief recap of the emission processes, which you very satisfactorily answered yesterday, that we are talking of continuum non-thermal emission from the lobes of radio galaxies. And as you correctly pointed out yesterday, that synchrotron emission is the process. And as you can see over here, that a steep power law of the optically thin emission is due to electron energy distribution, which is also a power law, and the synchrotron emission from electrons with a given energy in a given magnetic field peak at higher frequencies. Most of the emission comes at a higher frequency when the energy of the electron is higher. So if you have high energy electrons, they will radiate predominantly at higher frequencies, and you add up all the contributions from the electrons which are there at high energies to reproduce the spectrum which you see over here. So low energy electrons for a given magnetic field will generate most of their energy at lower frequencies, while higher energy electrons will generate at high frequencies. At higher frequencies, the electrons also lose energy more rapidly. So if there isn't a fresh supply of electrons, the spectrum will begin to steepen, and that also is an indicator of how old these objects may be, these lobes of emission may be. And optical thickness effects, the absorption can turn over at low frequencies due to either absorption by thermal gas or a process called synchrotron self-absorption, which Dipankar would have referred to in his lectures on radiative processes. And as we discussed yesterday, synchrotron radiation is linearly polarized. It's seen to be up to about 70% polarized in the lobes, but the radiation can be depolarized. For example, if the field lines are uniform, you'll get a high degree of polarization. But if the field lines are completely tangled up, then polarization will drop. Similarly, there is an effect called the Faraday effect of Faraday rotation, which can also lead to a decrease in the degree of polarization which you observe. So we'll talk a little bit about Faraday rotation later in this lecture this afternoon, but I would just like to keep this in mind. You have to keep this in mind when we come to it later. Now, you'd have also learned about inverse Compton scattering. I'm just mentioning these two primary processes because they'll be relevant in terms of the jets which you discuss. High energy electrons scatter off low energy photons, so the electrons losing energy while the photons gains energy. And I've just given an expression over here. The frequency would be gamma squared nu, so that if you had a radio photon at 1 gigahertz, then with an electron with a Lorentz factor of gamma, it could be scattered to about 10 to the power of 17 hertz. 10 to the power of 9 comes from here, and 10 to the power of 8, if a Lorentz factor is 10 to the power of 4, will come from here, giving you emission at high X-ray energies. So, but the photons which we are talking about over here can be photons which are in the radio source itself, but as you're well aware, the inverse Compton microwave background pervades the universe, and it's with a high temperature, higher redshifts, the energy density being larger. So inverse Compton scattering with microwave photons is also a significant effect, and that becomes particularly important when one tends to go towards higher redshifts. Okay, and these two processes both lead to loss of energy with of the relativistic electrons, because they're both losing energy, and the scattered radiation having a similar power law spectrum as that of synchrotron radiation. But the importance of whether the losses are due to inverse Compton losses or synchrotron losses depends on the ratio of the photon energy densities and the magnetic energy density. And as I mentioned a little while ago, the photons could be either synchrotron photons present in the radio lobes themselves, or it could also be the cosmic microwave background radiation. So with this little bit of an introduction, let us get on to what are we going to talk about today. Basically, we are going to talk about jets, which are the signatures of energy supply from the active galactic nucleus to the outer lobes of radio emission. Radio galaxies can be very small when they're young, when they're newly born. It could be just, less than 10 parsec or so. But on the other hand, they could slowly grow over time to some of the largest structures known in the universe. Pratik, who is one of your co-hosts today, focuses or studies intensively the large radio galaxies, which are referred to as giant radio galaxies. And with the current cosmological Hubble constant, it is put at 700 kiloparsecs from end to end when seen in projection. I've shown you an image over here that of a giant radio galaxy called NGC 6251, which is relatively nearby. The red marks the diffuse outer lobes of emission, and on different scales, you can see the jet which is supplying energy. When you can see in this image that when you observe a radio source with high resolution, when with antennas spaced very far apart, then you tend to miss the emission, which is more extended and diffuse. For example, when you look at it with VLBI scales, you only see what is tiny little bit in the nucleus of this galaxy. Whereas all the other emission, the technical jargon used is called resolved out. But basically what it means is that the Fourier components, when you transform the brightness distribution, is not something which you're sampling or picking up with the antenna separations that you have. So as a thumb rule, when the antennas are close by, or best even in a single dish, that you pick up the largest scale structures. And as you take your antennas far and farther apart in an interferometer, you will look at smaller and smaller scale structures and not be able to pick up the large scale structure. So when you take the antennas apart, you get high angular resolution, but you don't pick up the large scale structure. When you bring it closer, you have poor angular resolution, but you pick up the diffuse extended structure. So what kind of configuration you pick up will depend on what is the scientific goal of the observations that you're trying to make. Now, what I would like to point out over here, that in this particular source, which is true in a lot of sources, that the jets are highly asymmetric, though the extended lobes which you see over here are reasonably symmetric. So what we have is a situation where the energy supply seems to be one-sided, whereas there is evidence of energy supply on both sides of the nucleus. In this particular case, the small-scale nuclear jet, you can see the scales marked over here. This may have been done at a different Hubble constant, but to give you an idea, it's fine. This is about a parsec is what is marked over here. This is 100 kiloparsecs is what is marked over here. So you can see this is many orders of magnitude larger than what you see over here, but the energy supply is along the same channel on a very large range of sizes. So they're roughly aligned, but this is not always the case, and we may meet examples later, and I will sort of mention it then why that is the case. I will show you another image. This was an image which is made by Pratik, one of your co-hosts today. And but here you can see that the jets are symmetric. This is the optical galaxy over here, and this is the energy supply is symmetric. And also the outer extended lobes look reasonably symmetric. So the question is that why are some jets looking one-sided and some are looking two-sided? So that is, although the outer extended lobes, which are the manifestations of energy supply, look reasonably symmetric in both the cases. So we'll try to address that question, but before we address that question, I would just like to remind you of how fast the jets are moving, because that is relevant to the larger discussion of why these jets are one-sided. I will again remind you of what Gulab talked to you about, which is the motion of jets and he mentioned to you about superluminal motion. Now, if you want to measure motion of anything, what would you do? If you want to see how your friend is moving or how fast the car is moving, you would sort of look at two different times, the location, how much distance it has traveled, divided by the time, and you'll get a velocity. And that is exactly what you do over here as well. But here, because the objects are so far away, that the actual displacement in terms of angular sizes is extremely small. It would be at the milliarc second level, say. Now, to observe motions or displacements at the milliarc second level, you'll have to have observations of angular resolution of much better than that, so that you can actually monitor the motion. And to monitor the motion, you also need a clump or blob of emission. Otherwise, how do you actually measure what is moving if it is continuous and diffuse? So once you do that, this was done by radio astronomers in the early 70s, and this was what is called a very long baseline interferometry. And to get these resolutions, with the resolutions given approximately by the wavelength divided by the diameter, you need antennas which are spaced across the globe. There is something called a very large baseline array in the US, with telescopes spread across the US and in Hawaii as well. And then you have the European VLBI network, where antennas are spread all across Europe, and they combine that together. And there are also telescopes in China, Japan. The UTI radio telescope in India also participated in some of the early experiments. And you combine as many antennas as possible to make a global array and make these very high resolution images to try and monitor motion. For example, to give you an idea of the resolution, if you have a friend in Delhi, say, who is standing on top of Lal Kila and holds a 1 rupee or 10 rupee coin, you should be able to say what the structure of that coin is by sitting at Pune or so. So these are the kind of resolutions which we want to get, and we want jets with distinct features, as you can see, so that we can monitor their motion. Now, this is 3C273, one of the first quasars that was identified, and this is 3C279, which is also associated with a quasar. And I have also shown you over here the larger arc-second scale structures of these objects. So what you're seeing on the right-hand side is right in the nucleus over here, buried over here. It has a large-scale jet, and this also has a large-scale jet. This is 3C279, and this is 3C279 over here. This whole structure is buried right inside the core. And you can see that there are misalignments between the small and the large-scale jet over here, and we believe that these are due to projection effects. I will elaborate on that a little bit more in a short while. Okay. Now, when radio astronomers did this experiment, they were rather surprised to find that the velocities they got were much greater than the velocity of light. And radio astronomy was relatively new at that point of time, and the bulk of the astronomers were optical astronomers. And they said, well, they poo-pooed it, and they said, well, there must be something wrong. But this began to show up in more and more sources. And it was important to find a physical explanation for it in terms of the physics that we know, consistent with the special theory of relativity. And that is what a very nice and neat explanation was suggested. It had its roots in work done by Martin Rees earlier in the 60s itself. And we want to know how fast the jets are moving. Now, superluminal motion was introduced to you by Gulab. I will not derive the equations, but I will just try to illustrate to you conceptually what is happening, and we'll look at the equations in a short while to look at the implications of it. Now, let's get an intuitive picture of it. Now, what are we going to do? Let's say this is the nucleus. This is a jet which is coming towards you, the blob of plasma, which is coming towards you with a velocity v at an angle phi to the line of sight towards you. And when you measure distances, you always measure distances which are projected onto the plane of the sky. So even if the object has moved all this distance, what you're going to measure as a displacement is just as much, which is Vt and the sine of this angle. Now, how will you measure the time? Just look at it the way we are measuring time. So we will measure the time, say, when the object set off on a journey from here, okay, from the nucleus over here, and the wavefront or the ray of light which is emitted when it was at the core over here is something which will keep traveling and at a velocity of light and is coming towards you. Now imagine a situation where this object is actually coming at almost the velocity of light. Not quite, okay, not quite. It's a blob of plasma. It'll travel at a velocity smaller than the velocity of light in vacuum. But let's say that it is at a very high velocity, a very high fraction of the velocity of light. And let's say when it is here, it emits another wavefront. So what you're going to measure between the two time spans is this little time over here. So your time is getting squashed because this component is almost keeping up with the wavefront when you emitted it earlier, when it was emitted earlier. So now you're dividing distance by a very squashed time. So, and that is what is giving you an apparent velocity, which is much greater than the velocity of light. So special relativity survives. And this is a very neat and nice explanation of how you can get velocities which are greater than that of light. Now, this is the expression that the beta apparent is the apparent velocity, v is the velocity intrinsic to the source, and these are the angles of inclination. And phi is the angle of line of sight. Now, you can see that for a velocity, I've just put a number over here, that if it is traveling at 0.99 c at about 5 degrees to the line of sight, you'll get apparent velocities beta of the order of 6.3, which is 6.3 times the velocity of light. Now, let's look at this. You can only see superluminal motion when the object is coming towards you. You can only see it when it is moving at a very high velocity. Now, if you look at this expression, if phi is equal to 90 degrees, cos 90 is 0, sin 90 is 1, and you'll get beta apparent equal to beta. So if it is moving perpendicular to the line of sight of you, you will measure what is beta for the source itself. Now, when phi is 0, sin phi will be 0. Yeah, phi is 0, cos phi would be a small number. Cos phi is 1, and beta is 0.996. So you get a small number over here, but basically sin 0 is 0, so you'll get beta apparent equal to 0. So can you just physically think as to why, when phi equal to 0 degrees, that you will not measure your beta apparent is 0? Physically, can you just put an answer in Zoom chat? I'll just wait for 20 or 30 seconds to see what you put in, and then I'll try to answer the question. So when phi is equal to 0 degrees, I'm asking, why is beta apparent 0? Any answer, it doesn't matter. Okay. So I'll accelerate a little bit because nobody is responding today. That when the jet is coming directly towards you, we won't see any motion. Exactly. Okay. No. Actually, we wouldn't see any motion because you see what you're measuring is this is the displacement you need to measure. All right. If it is coming towards you. So Himadri has got the right answer, that we wouldn't see any motion of the AGN. So if you don't see any motion, then you can't measure velocity. You'll measure no velocity because it is coming directly towards you. So you'll not see any transverse motion. So there will be no velocity. All right. So Himadri, thank you for the answer. And now, what the other aspect which becomes important when an object is coming towards you, I will accelerate a little bit because I think I'm running a bit behind time, but we are sort of okay, I think. All right. That when an object is coming towards you, besides this effect of superluminal motion, the other effect which takes place due to the special relativistic effects of the solid angle being different in the rest frame and the observed frame, there will also be a frequency shift There'll also be a bandwidth shift, so because the clocks are going to be different. And if you put it all together, what you would get is that the observed intensity which you get can be enhanced by a large factor. Here, n is a bit model dependent, as we'll see later. It can be either 2 or 3. In the case of jets, usually 2 is used. And alpha is the spectral index, which we can take to be 1, is optically thin emission. And but if you know the precise value, you can plug that in. So you can see that this denominator over here, when it's traveling at a very high velocity at a small angle, and gamma would have to be reasonably high, okay, that you'd get a very small number over here. So that leads to an enhancement of the flux density. So not only is it moving superluminally, but it is also its flux densities enhanced. And if I were to go back to this picture, and that is precisely the reason as to why you get such very prominent cores over here, because inside these cores are the nuclear jets in which you observe superluminal motion, and because of their high velocities at a small angle towards the line of sight, their flux density is also being Doppler enhanced. So unlike a lot of the radio galaxies which you have seen, pictures which you have seen, and we'll see more of them later, that the cores are extremely strong. So when you measure superluminal motion, you automatically often have cores which are reasonably, or usually have cores which are reasonably prominent, and that is because of the enhancement of the observed flux density of the nuclear jets, which we saw in the case of NGC 6251, when the source is inclined at a small angle to the line of sight towards you. Okay. Now, let me sort of go back a little bit and just sort of reinforce that. That when it is coming towards you, you'll see superluminal motion, enhancement of flux density, but the velocities, and the more pronounced it is, the velocity will be larger. More pronounced it is when the velocity is larger, both in terms of the enhanced flux density and superluminal motion. You can work out yourself by seeing at what kind of phi it maximizes for different values of beta. You can play around with that equation and look at it yourself. And this little book over here, which I mentioned, the actual hard book which is published is very expensive, but there is an online version of it here, which is free. And NRAO, the National Radio Astronomy Observatory in the US, has made this widely available by an agreement with the publishers. And you'll see some of these things, aspects being discussed there quite nicely as well. Now, sorry, I went ahead a slide. Now, let me just go back to this over here. Now, Doppler boosting of observed flux density. Now, let's come back to this equation over here. We saw this image of 3C273, where we superluminal motion, and we also had earlier met this galaxy 3C296, which has a weak core and very symmetric jets. Now, look at it over here when I mentioned about the enhancement in the flux density for an approaching jet. Now, in this particular instance, what happens is that although the nuclear jets start off with velocities very close to that of light, it can slow down as it moves outwards, advancing its way, pushing its way through initially the interstellar medium of the host galaxy and later at the intergalactic medium. Now, let's just look at this equation for a little while and see what happens when phi is equal to 90 degrees. When phi is equal to 90 degrees, you'll get cos 90 is 0, but you'll see that even at 90 degrees, cos 90, then S, the intrinsic, would get divided by gamma to the power of n plus alpha. So even a source which is at 90 degrees to the line of sight, its flux density would get diminished. It will not get enhanced. Enhancement occurs when it is coming towards you. It is more pronounced when it is at small angles to the line of sight. For example, if you take cos 0 degrees, it is coming directly at you. You may not see superluminal expansion. As Himadri pointed out, that there is no transverse motion, so you're not going to see motion. You are not going to see displacement, but you're still going to see enhancement of flux, because beta is there, which is very close to that of light. So your 1 minus a very high number will give you a very small number. You multiply that by gamma and raise it to cube or n plus alpha, depending upon the spectral index, and you'll get a large enhancement in intensity. So when you go further away, the flux density diminishes. I put blue for approaching and plus for receding, and when it goes away, the flux density is going to diminish. So what is the inference over here? We will try and look at it in a very short while. But just remember these two particular aspects. So if I were to use what is called the relativistic beaming model, then the ratio of a component which is approaching you to the ratio of a component which is receding you, that is basically the ratio of the two equations which I wrote down earlier, would give you a ratio which is given by this expression, 1 plus beta cosine phi divided by 1 minus beta cosine phi, whole thing raised to the power of n plus alpha. N could be 2 or 3, as we have mentioned. Now, I've just put two sort of canonical numbers over here, that if the velocity is of the order of light, close to it, phi is of the order of 20 degrees, the flux density ratios could be in thousands. Orders of magnitude could be the flux density ratio. So if the nuclear jets or jets are moving at high velocities, the ratio of the flux density or brightness of the one which is coming towards you would be larger than the one which is going away from you by a very large factor. If you look at phi equal to 90 degrees over here, it's going to be 1. So at large angles, this ratio is less. So for sources inclined at large angles and low velocities, it is going to be smaller. So if I go back to this figure, then the inference over here would be that in the case of 3C296 and the giant radio galaxy, which I showed of Pratik's image, that the jets are symmetric. That means the jets in these cases are moving at relatively mild velocities. It could be mildly relativistic, it could be 0.1, 0.2, 0.3 C, but the effects are definitely less marked than something which is traveling at 0.9 C or 0.8 C. So when you see a one-sided jet, it is moving at a small angle or smaller angle and a high velocity. And when you see a symmetric jet, that it is moving at a large angle and at a small velocity. So this would be the canonical sort of picture which we will try to see how far it sort of holds up and whether it holds up at all. Okay. Now this we have covered, so I will try and go to the next aspect of it. And in this slide, what I'm trying to do is that I'm trying to pose you a question, okay? And why are the lobes with the hotspots reasonably symmetric while the jets appear one-sided? So Sagar, our host, has set up a poll. I will just activate the poll, and I think there are 3 answers over there. I'll launch the polling, and you can fill up the answers, and let's see how the answers go, okay? The poll should show up on your screen. I'll leave it on for a minute. The question is, why are the lobes with the hotspots reasonably symmetric while the jet appears one-sided? In this particular case, it's a quasar. It has a very one-sided jet. The lobes are inclined at large angles to the line of sight, while jets are at small angles. So there's only one answer right now. So I will wait for a minute. So I'll urge more of you to fill up the answers. Okay. Some more. Some more. Okay, I'll put it on for another 10 seconds and then we will stop. All right. Okay, we'll stop now, and we'll stop now. All right. Now let's look at what your, okay, I'll share the results with you. Okay, share results is showing, so I'm going to share the results with you, and I'll discuss the different answers that you've suggested. Okay, the lobes are inclined at large angles to the line of sight, while jets are at small angles. That answer, although most of you have opted for it, 22 out of 37, is not the right answer. Now, why is it not the right answer? Because if you take a source, say, just imagine a source, look at your pencil. Let me say that you take a long tin rod or your pencil or your pen, and jets are flowing out along the axis of the stick or pen which you have, and the lobes are forming at the outer edges. So you cannot have a situation in the odd case when the whole energy supply due to precession of the jet axis or some interaction with the galaxy may have changed the axis of ejection of the jet. They could be at different angles. But you can see that this is a reasonably linear structure, collinear structure. So it is very unlikely that the jets and lobes are at different angles. In fact, you can see that the jet is beautifully connecting to the core. Some instabilities can develop as it enters the lobe, sometimes even along the way. So you see a bit of a sort of twirl at the end, but they are all roughly along the same axis, right? Okay, now the hotspots and lobes are not moving. Now, this is not correct. The reason is that they're moving. What happens is that the jets are squirting out at high velocities, as we saw. They're moving out at relativistic speeds, but they are actually trying to push its way, interacting with the interstellar medium and later the intergalactic or intercluster medium that they encounter. If they're moving at supersonic velocities, which is true of these large high luminosity one-sided jets, then they will form a shock front because the speed would be greater than the sound velocity of the medium. It'll form a bow shock, and that will try to snowplow its way through the interstellar medium, balancing the momentum flux density in the beam with the ramp pressure of the external medium. So it is moving outwards, but it is moving outwards at a velocity which is very mildly relativistic. In some cases, it is less than 0.1 c. Estimates vary quite a bit depending upon whether you're talking about the low luminosity Fanner-Rayleigh class 1 objects or the high luminosity Fanner-Rayleigh class 2 objects. So what is happening over here is that this is a hotspot where the jet is interacting with the external medium. There is a bow shock over here, and the material is then flowing backwards to form these extended lobes of emission. So these are moving outwards, but they are roughly symmetric because their velocities are much smaller. So you can later do these sums yourself and see that if you had just velocity of 0.05 c, say, and an angle of say about 40 or 45 degrees, what is the kind of ratios that you would get? You can just play around substituting numbers over here, and you will see that for very mildly relativistic velocities, maybe less than 0.1 c or 0.2 c, that and reasonably moderate or large angles to the line of sight, you're going to see velocities which you got flux density ratios or lobes which are reasonably symmetric, right? So that is the answer to that query, and which you took part in the poll. Now, in the small scale jets, we can measure the velocities. Now, in science, you want to be absolutely certain that what you're trying to explore is correct. It is a plausible hypothesis you start off with, and you try and find more and more evidences to support what you believe, all right? Or what you think may be the right scenario. Now let's look at this particular source over here, okay? This particular source over here. We are trying to say that the nuclear jets where we can measure motion, we can understand superluminal motion in the core-dominated sources by saying they're coming towards us. The enhancement in the core flux density is consistent with it. And the nuclear jet is also pointing in the same direction as a large-scale jet, roughly. Misalignments can be understood in terms of projection effects. When you project two vectors back onto a plane perpendicular to it, you can get large misalignments, but whatever evidence we have, we see that the large scale and the small scale jet are in the same axis. So it's natural to assume that this asymmetry which you see in the large scale jet is also due to a similar physical reason of reasonably relativistic velocities of the jet. So let's say it starts off with 0.99 c over here. It could be 0.7, 0.8, whatever times the velocity of light. Here, as we saw, it could be much smaller. So even with about 0.8 c, if you play around with these equations, you will get very large ratios consistent with what you observe. So there is a consistency argument. Okay, now we want to see, can we stretch this further? So what are we going to do? I'm going to describe to you in 5 minutes a very nice test which was done to show that these jets are actually also on the approaching side. So if it is on the approaching side, then we can hold our heart in our hands and say, oh, that explanation must be correct. Now, to do that, a very nice test was done by Simon Garrington. At that time, he was a graduate student at Jodrell Bank, and Robert Lang, who's been one of the leading lights in studies of extragalactic radio sources, and it is often referred to as a Lang-Garrington effect. So what we're going to look at is, for example, if the source is inclined at a small angle, not maybe 5 degrees, but maybe 30 or 40 degrees, and let's say you're observing from here, all right? And this is on the receding side, and this is on the approaching side. And we learned that this is associated with a quasar, but quasars also have a large host galaxy associated with it. So what will happen is that when you're observing from here, this material is going to travel through this host galaxy, whereas this lobe is not going to travel to this host galaxy. The host galaxy will have stars, will have the interstellar medium, will have magnetic fields. So it has a magneto-ionic medium. So if our explanation is correct, let's see what is the manifestation or what is the result of that. What is the result of that? To understand that, I will just briefly mention to you the concept of rotation measure. Electromagnetic radiation, this is something which you would have done earlier, of wavelength lambda has its plane of polarization rotated as it travels through a magneto-ionic medium. The degree of rotation, by how much it changes, is proportional to the square of the wavelength, and the electron density and the parallel component of the magnetic field integrated over the line of sight. Okay, so if you make your observations at a longer wavelength, which means at a lower frequency, that these waves are going to, the vector, the polarization E vector, will turn around much more. Similarly, if the electron density is higher, or the parallel component of the magnetic field is higher, or there is a larger path length of travel through such a medium, you will get a larger amount of rotation. All right. Now, the integral is what is referred to as the rotation measure and measured in units of radians per meter squared, so that if wavelength is in lambda squared, so the amount of rotation which you see will be given in radians. And that is a measure of the NE and B parallel component, the product of it integrated over the line of sight. Let's see what happens now. What I'm trying to show you over here is the manifestation of it. Now, for example, on the top right-hand corner, you see a radio source which we are observing. And let's look at the figure over here on the left lower side, where I say it's a homogeneous medium. Now, in a homogeneous medium, let's say if the signal comes from different little portions of the radio lobe, they will go through it. If NE is uniform all across and B parallel is uniform all across, from all the different bits of the source, that the E vector will be rotated by the same amount, so that when you add it up, it'll be similar, all right? But on the other hand, nature is hardly homogeneous. It has all kinds of irregularities of different scales. There will be different values of magnetic field around different lines of sight and different electron densities. And this is what I'm trying to illustrate to you over here. Now, different parts of the source coming through, passing through slightly different path lengths over here are going to experience different degrees of rotation. And that will be compounded when you observe at longer wavelengths. Lambda squared dependence, as you can see over here. So when for that particular lobe, you average it out, average out the vectors which, because of its different path lengths, are rotated by different amounts, you will get a net drop in the degree of polarization. So earlier we saw that in the source itself, as the field is very tangled, you'll get a degree in the drop of polarization compared to the theoretically expected values. Similarly, if it passes through a medium like this with irregularities of different electron densities, and you average them out, you will get a drop in the degree of polarization. The drop in the degree of polarization is stronger at longer wavelengths because the rotations of the E vectors are much more. This is referred to as side-to-side depolarization because you're sort of sampling emission originating from different sides of the source, different parts of the source, side to side. And this is like a screen in front. But you could also have a situation where, in addition to the synchrotron emitting plasma, a relativistic plasma, you could have a thermal magnetoionic medium within the radio source itself, in which case emission coming from the back of the lobe will be rotated more coming from the front of the lobe, and you could get what is referred to as a front-back depolarization. But for this course will just focus on this. Usually, the amount of thermal material within the lobes is very small, but we will just focus on this, where there is a screen, which we talked about as the galaxy, the interstellar medium of the galaxy. So what you expect in this is as follows. That the lobe which is coming towards, traveling towards through the interstellar medium of the host galaxy will get depolarized much more when you sort of average it out and compared to the one which is approaching you. Now, these are two images of a quasar again called 3C47. 3C is the third Cambridge survey. And I've shown you two images as condor plots, one at a wavelength of 6 centimeters on the left-hand side, and the one at 20 centimeters on the right-hand side. Now, 20 centimeters also is a longer wavelength, so it is going to get rotated much more. And if it is going to get rotated much more, that when you average it out, there's going to be a drop in polarization. So what you see over here, like porcupine-like thing, which if you saw my head yesterday, my head was looking like that with the hair standing up, is that this is, you don't see hardly any vectors over here at all. And that is because the degree of polarization which you see at 20 centimeters is much smaller. Here, the length of the vector is proportional to the polarization percentage, and polarization percentage, or the ratio of polarized intensity total intensity, and the length of it and the angle of it gives the orientation of the E vector that you observe. So you can clearly see that the lobe which is going away from you is more strongly polarized. You can plot it in a slightly different way as P20, degree of polarization 20 by 6 centimeters, and you can see these values are lower. So that actually tells you in a very nice way that indeed these jets are approaching you. So today there is a consensus of view among the community that the large-scale jets, although we cannot directly measure the velocity, that their apparent one-sidedness is also due to relativistic motion, maybe not as high as the nuclear jets, but still highly relativistic to explain the observed brightness asymmetry of these jets. The outer hotspots over here, which you can see, they're plowing its way through the interstellar medium of the host galaxy or the external medium it encounters. And as it is pushing its way, balanced by the ramp pressure, which is rho v squared of the external medium, and the momentum flux density of the beam, that it is moving outwards, but at relatively small velocities, as we just discussed a little while ago. Briefly, we have been concentrating at radio wavelengths, but jets are ubiquitous. We will not, we want to talk on unification schemes, so we'll not spend too much time on this. At other wavelengths as well. In fact, the jet in M87, although it was not recognized as a jet, was seen as early as 1908 by Curtis, who noticed a wisp of light, which you know today is a jet. And jets are seen at X-ray, radio, optical wavelengths. A large number of quasar jets have been mapped at X-ray wavelengths. And these are the jets of M87 at Chandra, VLA, HST images of it, X-ray, radio, and optical. There are differences, and it's interesting to understand what the differences arise due to. This is perhaps a shock front in the flow of the jet, but the spectral energy distribution can largely be understood in terms of synchrotron radiation itself, with the energy of the electrons extending to the highest energies. Similarly, just as in this nearby galaxy M87, I'm going to show you the jets of the quasar 3C273 at optical, X-ray, and radio wavelengths. Okay, here the physical processes are such that inverse Compton scattering is believed to play a role in trying to understand the spectra of across the wavelengths from radio to X-rays. And as of now, as far as I understand it, inverse Compton with CMBR photons is the favored explanation. So this is as far as jets are concerned, and the asymmetry, as we saw, is due to relativistic motion of the jets, and we can understand both superluminal motion and jet asymmetry and flux enhancement in the framework of special relativity by invoking the hypothesis or the scenario which we just mentioned. So in the last 10 or 15 minutes at the most, I will try to introduce you to this concept which we talked about earlier, that can this be used to reduce the observed diversity of at least some sections of the active galactic nuclei, which we talked about and which you have met earlier from your own readings or earlier lectures in the refresher course in summer school. On the left is a radio galaxy, which is 3C452. This image was made by Sumana Nandi, who's also one of your hosts today, monitoring the YouTube. And you can see that it has a relatively weak core. This is the core over here, relatively weak core. Most of the emission is from the extended lobes of emission. These are optically thin emission. That means they're not absorbed, and they're diffuse and they're extended. And these extended lobes, as we mentioned, can extend up to several megaparsec in size. And the spectrum, as you can see, is optically thin. It's a straight spectrum over the region over which it has been measured. On the other hand, look at this object, which is a quasar 3C454.3. These are all strong sources from the third Cambridge catalog. You can see that it has a one-sided jet, and its entire emission is dominated by the nuclear component. Okay, nuclear component, and you can, when you observe this with higher resolution, you can see a nuclear jet over here, which is buried in this nuclear or core component. And because the nuclear or core component are compact, residing right in nuclear regions of the active galaxy, they can be affected by both synchrotron self-absorption and free absorption by dense thermal gas in its vicinity. So they have often complex or flat spectra due to the absorption effects, and you can see the effect of that in the spectrum on the right-hand side. So we have core-dominated flat spectrum objects, and we have lobe-dominated steep spectrum objects. Now, given our discussions earlier today, that we see a prominent core when the nuclear jets are beamed at us, and we see a weak core when it is inclined at large angles towards the line of sight towards us, then we are quite sort of in our right minds if we ask ourselves the questions, hey, are these the same kinds of objects? We are just seeing it at different angles to the line of sight. In nature, in the universe, objects will appear inclined at all angles to the line of sight towards you randomly. We don't have any preferred position in the universe. The universe, these galaxies don't particularly know we exist. They will just radiate in random directions. Now, then you ask yourself that not only the radio properties, but all other properties have to be consistent with this scenario. So this whole scheme of trying to understand at least some subsets of apparently different kinds of objects in a similar theoretical framework is what is referred to as a unified schemes for active galactic nuclei. Why does the source on the right have a flat spectrum? Why does the source on the left have a steep spectrum? These are questions which we have tried to address. What I want you to quickly put in the chat box is which source will be detected more easily in low frequency radio surveys. Okay, which do you think will be detected more easily? So I'll give you 20 seconds because it's left or right. And we didn't have a poll for this, but it doesn't matter. Some of you can just type your answer and we will, in 20 seconds is all you have. Which source will be detected more easily in a low frequency service? For example, with the GMRT, where there's been a huge survey done at 150 megahertz called the TIFR GMRT Sky Survey, TGSS. Okay, left. Very good. Rutwik says left. Rahul says left. Fantastic. Okay, so left it is. All right. So left it is, and that is because at low frequencies, these objects, so Saikia also says left, fantastic. So left, these are the objects which will be picked up, just one says left. So these are the objects which will be picked up in a flux density limited survey at low frequencies. These will be more easily picked up in the high frequency surveys to a given flux density limit. If you go very weak, very high frequency surveys, these may well be below your flux density limit, whereas these will come up. But if you do a high frequency survey, although all these objects are randomly distributed, you may preferentially pick up more of these objects just by a selection effect. Okay. Tamals also say lobe dominated. Excellent. So this is very good. Now, just to revise and recap before we touch on the scheme of unified schemes, we'll take 10 more minutes at the most, and then we'll stop. Radio cores at flat spectra resolved into nuclear jets, superluminal motion when nuclear jets are inclined at small angles, nuclear jets moving at velocities close to light, approaching jets, flux density Doppler boosted, flux density receding ones, Doppler diminished. Okay, more asymmetric jets and sources inclined at small angles, co-dominated sources, more strongly variable as well, because small changes in phi or velocity will get amplified when you observe it. So this is the scenario we have now. We will first concentrate for 5 minutes on the radio loud objects, then we'll concentrate for a few minutes on the radio loud objects, and then we'll summarize and close. Radio loud objects are very luminous in the radio, and that is on the upper part of this figure. Now we are saying that the superluminal sources are generally quasars. They tend to have stronger cores. They have to have more asymmetric jets. So they would be inclined, as you see over here, at small angles to the line of sight over here. Small angles to line of sight towards here. So when you look at it at large angles from here or from here, then you're going to see the effects of what you see in the radio galaxies. You'll see weak cores.
Sagar?
Yes, Pratik.
Can you hear Saikia?
No.
Can you please check?
Okay.
Can you hear me now?
Yes, sir. We can hear you.
Okay, okay, fantastic. All right. Okay, sorry, my internet connectivity went for a short while. Okay. Now, so let's get back to where we were. So you can see that when you see at a grazing angle, you see a broadline radio
I
galaxy.
think you need to
When
share
you
your
see at a
screen.
small angle, you'll see a narrow line radio galaxy. And if you see it at very close to the, or reasonably close to
Check
the,
you need to share your
sorry?
screen, I think. We don't see your screen.
Okay. Okay, 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 okay. Okay, let me see what happens. 1 second. Okay. Okay, where does it come? It's not coming up. 1 second.
Just share your screen.
Yeah, that's what I'm trying to do. Speaker view. Okay, yeah, share screen. Is it okay now?
Yeah, just do full screen and yeah.
Right, great.
Yeah.
Okay, okay. Thanks. Thanks. I'll just go back to from current slide. Is it okay now?
Yes.
Okay, thanks a lot. Yeah. So sorry for the disruption, but yeah. Okay. Now, so this is where we were, that at small angles, it will be seen as a quasar. And that also provides a natural explanation how the quasars have broad lines which you observe. Whereas when you look at a radio galaxy, particularly a narrow line radio galaxy, you don't see the broad lines at all. And somewhat at an intermediate angle, you may see the broad lines in a radio galaxy as well. So that provides a consistent explanation of the radio loud galaxies and the quasars. Now the question is again, remember the Fandorf-Rayleigh class 1 and class 2 objects? One has the class 2, the high luminosity ones which have hotspots, whereas the Fandorf-Rayleigh class 1 objects have diffuse extended lobes of emission. By just changing the orientation or how you incline it, you cannot change an FR2 into an FR1. So you need two different schemes. And the current consensus is that the beamed counterparts of the Fandorf-Rayleigh class 1 objects are the BL-lag kind of objects, which we talked about earlier, where you don't see the emission lines at all, but you see diffuse structures similar to the FR1 radio galaxies. And the reason why you don't see the emission lines at all while you're poking your nose right into central region is because the continuum itself is so strongly beamed that it overcomes it's more intense than the emission lines which you would have normally seen. So that is one possible explanation. There could also be cases where there's very little gas, etc. But the fact that a beamed component can actually sort of swamp the emission lines is something which one has observationally seen as well. So that is consistent with the observations. Now, there's a lot of questions as to what is a torus, why should it be there, and what is the observational evidence for it. So we'll not be able to touch on all the aspects, but let me just touch on the observational evidence for torus. Okay, and then I'll briefly talk about the FR1 objects, and then we will close. We're overrunning a little bit, but we will finish very soon. Okay, now let's look at this. You have a torus of material, you have the black hole and the accretion disk over here is generating a lot of high energy photons. Photons are not able to go out uniformly along all axes. They'll be confined to a cone. And because they're confined to a cone, can we see cones of ionized gas in the vicinity of the nucleus? So if we can see cones of ionized gas in the vicinity of the nucleus, we will say we believe in this scenario, at least it is consistent with this scenario. Okay. Something which you've seen before. And this is images of a Seyfert galaxy. And you can beautifully see when you look at the HST observations over here of the cones of ionization lending support to the fact that there's a torus sitting in the central regions of these galaxies. Okay, there are other examples as well. These are ESO observations of relatively nearby galaxies. It is easier to image these in relatively nearby galaxies because of the resolution which you require, and ionization cones, which you see over here, ionized by hard photons from the nucleus. And you can also sometimes see evidence of the torus In this case, this is another Seyfert galaxy, NGC 4151, where evidence of a molecular torus is seen right in the central region of the galaxy. So we have a torus which affects the optical spectra which you see. It also affects properties at other wave bands, but that is not something we'll have time to talk on. So the last theme which I will sort of touch upon and then we'll close is the radio quiet part. Radio quiet part relates to the unification of radio weak or radio weak active galactic nuclei. These are much less luminous by an order of magnitude or more compared to the standard radio galaxies and quasars which we saw. And in this category, we are going to discuss the two types of Seyferts. If you recollect from yesterday's presentation, at Seyfert 1, you see the broad lines, and in Seyfert 2, you don't see the broad lines, you see the narrow lines. Seyfert 1, you'll see the broad lines as well as the narrow lines. Seyfert 2, you see only the narrow lines. So invoking a similar kind of scenario, a similar kind of torus whose evidence in Seyferts we have seen a little while ago, and there's been some evidence of that even in radio galaxies, that you can understand that the dichotomy between these two types of Seyferts as just being dependent on orientation. Seyfert 1s are inclined at small angles to the line of sight. Seyfert 2s are inclined at large angles to the line of sight. All right? Now, now the question we'll ask ourselves again in astronomy as well as in all science, to really sort of validate something, you need more and more pieces of evidence to convince people. So can we peep in and to see if there is really a Seyfert 1 nucleus in a Seyfert 2 galaxy? And if you were to sort of do that, how would you go about it? How would you peep into a Seyfert 1 nucleus to see if it has a Seyfert 2 galaxy? So if you'd like to sort of give any suggestions in the chat, I will just wait for 20 seconds, but because time is short, but I will otherwise carry on. Okay. So any suggestions of how you might peep into a galaxy? Clearly, we can't go around, we can't travel there. So we have to find interesting and clever ways of peeping into the nucleus of a Seyfert 1 to Seyfert 2 to see if there is indeed a broadline region over there. If you think of your friend hidden behind a wall, one way you could see him or her is how? Well, since there are no answers, well, if you had a mirror, right? If there's a mirror suitably located, you'd be able to see it. So let's see what are these mirrors which can happen on a cosmic scale. All right? Okay. Now, on the mirrors which can happen in a cosmic scale are that in the vicinity of the nucleus, where you have these narrow ionized gas, the nuclear cones which I mentioned about earlier, is there something which is fortuitously located that you might be able to reflect light from the hidden nucleus by these ionization cones into your line of sight? And how would you know actually that it is actually reflected light? How would you know it is reflected light? Now, let's see how we might know whether it is reflected light. Once you would have studied in your basic physics about how reflected light gets polarized. And so what we are looking for is broad emission lines, because broad emission lines, you need a supermassive black hole at the center. So they cannot occur elsewhere in the galaxy. They will have to be from the center. And also the lines will have to be polarized, because if it is reflected, and reflection can produce polarization, whereas the lines by themselves are thermal processes, and that's not going to be polarized. Now, here is a very clever experiment which was done by a number of astronomers. Antonucci was also one of them. I've got later plots from here, but this is an image of this galaxy which I showed you earlier. This is the total intensity, and this is the polarized intensity, where you can see the broad lines which were not visible in total intensity. So to show it as a cartoon over here is that you have the broadline region which is hidden. If the broadline region is hidden, if the gentleman is looking from here, you would see it as a Seyfert 2 galaxy. If this galaxy was turned around, you'd have directly seen a Seyfert 1. But if there is clouds of dust or electrons scattering light into his line of sight over here, then you would be able to see the Seyfert-1 nucleus. So we indeed have observational evidence for a reasonable number of Seyferts that there are indeed Seyfert-1 nuclei lurking in what appears to be Seyfert-2 galaxies, lending additional support to the hypothesis that the actual diversity of AGN is also generated by the effects of orientation and relativistic beaming effects.
Saikia, sorry to interrupt you. We have to wind up because we have the colloquium today at 4.
I'll finish in 2 minutes.
Yeah, sure. Thanks.
2 minutes. 2 minutes, I'll finish. Okay. Now, I'll just go to the last 2 slides and we'll finish in 2 minutes. And then you can ask me a few questions and you can also email me later if you like. Estimate of size. One thing we want to know is how close the emission lines are. We again have mentioned that because of the effect of the broad lines, we can understand in terms of the effect of the mass of the black hole. They're very close by. We can also do it in terms of the variability of the line, variability of the continuum and the lines. When we look at the continuum variability, as we can put a length scale on it, since signals can travel at most of the velocity of light, and as you can see, this is extremely small. And because of changes in continuum variability, the lines will also vary responding to it. And you can see over here in this plot that the broader lines, there's a velocity weight of the lines which are closer to the nucleus, the lag is much less. So you can use these arguments to also estimate the sizes of black holes. So we will close with a summary which says that there is a fair degree of success in understanding the diversity of AGN in terms of the effects we discussed. And just a summary sheet over here. It's not that there are no problems, there are challenges, there are interesting objects which defy the norm, but overall, there seems to be a broad agreement in terms of that geometry and orientation play a significant role along with relativistic motion in trying to understand the physics and also the variety of active galactic nuclei. Here, the large angles are put in green and the small angles to the right of sight I put in orange. And as I mentioned, you cannot turn an FR1 into an FR2 or a Seyfert with a host galaxy into a radio galaxy. So you need different kinds of unified schemes to understand the dichotomy in these different categories of active galactic nuclei. So I will stop there. Santosh and Sagar have also got to run the colloquium, but maybe just a few questions we can take.
Yeah. So there are just 2 questions, one here and one on YouTube. So I'll just make it quick. So Darren Wilson has a question. Is Hawking radiation proven? And does that have any effect on the jets?
Hawking radiation is actually, in terms of the energies that you're talking about, it is very small. Okay. Here, actually, the energy is generated more by accretion, the huge amount of energies which you see. Okay. Huge amount of energies which you see are due to a conversion of gravitational potential energy into other forms of energy. Accretion is the only process by which we can understand the energetics of these highly luminous objects.
Okay.
Next question.
Yeah, the YouTube question is by Madhusudan Purohit. He's asking why jets have knots and why is it not continuous? And what is the distribution of the velocities of the particles in the jet and its significance?
Okay. Okay. Actually, there are 2 motions over here. There are multiple motions over here. Okay. Now, one is of course the relativistic electrons themselves, which are moving at highly relativistic velocities to generate the synchrotron emission which you're seeing from the jets. So that is the motion of the relativistic electrons themselves. But in addition to the relativistic electrons which are zipping around at ultra-relativistic speeds, is the bulk motion of the material, which is transporting energy to the outer lobes and traversing outwards. Now, there are various ways in which knots of emission in the jets can be generated. There could be shocks in the flow of the jet. There could be instabilities in the flow of the jet. And the energy supply also may not be continuous because when we monitor some of these objects continuously for long enough time scales, we find that a new blob of emission appears. just as you saw in the image which I showed you, where superluminal motion has been monitored, that you'd find that there is a change in flux, there's a new blob which is coming out, and then you keep monitoring. So not only instabilities in the flow, shocks in the flow of the jet, but also new plasmons which are being born in the nucleus would give you rise to knotty structures. And besides that, also, in addition to these features, there could be just patterns in the flow of the jet. So there's a lot of debate whether some of these features are actually pattern flows or whether they're actual flows. But there are a variety of ways in which you can generate the features which you see in the jets. So we can stop there probably?
Yeah, I think we can wind up here. Thank you for the lecture. It was really nice.